Welcome to today's lecture. A couple of days ago, we started a series on radioactivity. We stopped the series at part 3, and part 3 stopped with an exercise. I asked that you take this exercise up. Having done one for you, I wanted you to see if you could replicate what I did. So this was the question I asked you to attempt. A radioactive isotope. A radioactive isotope 23892 decays by emitting 2 alpha particles, 6 beta particles, and a gamma ray. What is the number of neutrons in the resulting daughter element? So we're given uranium-238 92. We're told that it decays by emitting, take note of these, 2 alpha particles, 6 beta particles, and a gamma ray. So then, we start by writing the radioisotope 23892, emitting 2 alpha particles. Don't forget, alpha particles are helium nucleus. So we use helium to represent alpha particles, multiplying it by 2 since we are told it emits 2 alpha particles. And so 2 times 4, 8, 2 times 2, 4. So we have 238 minus 8, that will give us 230. 92 minus 4, that will give us 88. So this is the new daughter element. You will transfer this to this other side because we're told that it further emits 6 beta particles. Don't forget, beta particles are fast moving electrons, and we represent beta particles by using the symbol E0 minus 1. Don't forget, we're told 6, so you multiply it by 6. So 6 times 0 is 0. 6 times 1 minus 6. So 230 minus 0 is 230. 88 minus 1 minus that's plus, that's 88 plus 6, that will give us 94. A new daughter element B is then transferred to this point, and finally we're told that it emits a gamma ray. This is the symbol for gamma ray. And so we just take 230 minus 0, that gives us 230. 94 minus 0, that gives us 94. You need to commit the symbol for alpha particle, commit the symbol for beta particle, commit the symbol for gamma ray to memory. You commit it to your memory so that anytime you hear alpha particles, you just remember it is helium nucleus. Anytime you hear beta particles, you know you're talking about fast moving electrons. Anytime you hear gamma ray, you know you're talking about electromagnetic radiation of very short wavelength, and then it is represented this way. Now, the final daughter element has atomic number 94 and nuclear number 230. So your proton number, which is otherwise known as atomic number, is 94. Your nuclear number, otherwise known as mass number, is 230. So to get the number of neutrons, you will subtract the proton number from the atomic number, which is the number of protons, the proton number. Sorry, you subtract the proton number from the nuclear number, I beg your pardon. And then when you do that, you get the number of neutrons. This will take us to neutron-proton ratio. The neutron-proton ratio. The neutron-proton ratio is used to determine whether an atomic nucleus is stable or unstable. Look at it. The neutron-proton ratio is a key factor that determines whether an atomic nucleus is stable or radioactive. So what's the formula? Neutron-proton ratio, as it implies ratio as number of neutrons to number of protons. For a radioactive element, that is, for an atomic nucleus that is unstable, the neutron-proton ratio is less than 1 or greater than 1.5. However, for stable nucleus or non-radioactive element, the neutron-proton ratio lies between 1 and 1.5. However, for some stable nucleus, you could have exactly 1 as a neutron-proton ratio. A good example is calcium with atomic number 20 and mass number, nuclear number 40. So if you do that, you're going to get 1. So sometimes the neutron-proton ratio could be 1. But generally, we're saying that once the neutron-proton ratio lies between 1 and 1.5, we say that the atomic nucleus is stable or non-radioactive. So let's see some examples. Radioactive element, that is for an unstable nucleus, we're using uranium-238, 92. Number of protons, 92. Number of neutrons, 238. So minus 92, and that will give us 146. That is the nuclear number minus the proton number, that gives us the number of neutrons. So our neutron-proton ratio, number of neutrons over number of protons, that will give us 159. Remember, we said for an atomic nucleus that is not stable, the neutron-proton ratio is either less than 1 or greater than 1.5. This value here is greater than 1.5, so it means that the atomic nucleus is unstable. So it means that uranium is a radioactive element. For an atomic nucleus that is stable or a non-radioactive element like sodium, the number of proton 11, number of neutrons would just be 23 minus 11. That is the nuclear number minus the proton number, that gives us 12. So if we take up the neutron-proton ratio, we have 12 over 11. That will give us 1.09. Here, the value lies between 1 and 1.5. So we say that this atomic nucleus is stable, is a non-radioactive element. This will take us to instruments used for detecting radiation. The first instrument is Geiger-Müller counter. This works by ionization of gases in the tube. Number 2 is scintillation counter. It uses materials like zinc sulfide or sodium iodide to detect light, which is then converted to electrical impulses or signals. So let's see it. It uses materials like zinc sulfide or sodium iodide. Light produced is converted to electrical signals, which is then read on the counter. The third one is diffusion cloud chamber. Radiation here enters the chamber and then ionizes air and causes condensation of vapor. This will take us to part 5. We just concluded part 4 now.